Suppose you're implementing the k-means algorithm. How do you select the optimal k value? Hi everyone, welcome back. We're here today with Vikram for another machine learning mock interview. Vikram, would you mind introducing yourself for our viewers?
Yeah, definitely. My most recent experience has been as a senior machine learning engineer at Meta, working on ranking and recommendation systems.
Okay, amazing. So without further ado, our question today is, suppose you're implementing the k-means algorithm. How do you select the optimal k value? And before we get started, be sure to click the link in the description for Exponent's machine learning interview course. We have a ton of content to help you ace your next ML interview, including expert coaching, peer-to-peer interviews, and more. All right, Vikram, take it away.
Great. So just to set the context of the question itself and elaborate a little bit more, and so we're on the same page and I'm answering the question that you intend me to. So as I understand it, k-means clustering is a technique used for finding clusters in a data, typically data in a high dimensional space, and we are interested in locating centroids or clusters that are within the data that allows us to learn a few things, especially within social media networks and so on.
Mhm.
There could be clusters of various kinds of users with various kinds of profiles or usage usage patterns.
Yeah.
So that's a typical understanding of this.
And
Um,
could you tell
yeah.
me, is it an unsupervised or a supervised problem?
Yeah, thank you for asking that. It's an unsupervised problem, right? You actually have data and you want to look at the data itself and find the properties in the data without any specific labeling to it. The the distance or a metric that you define on that set of data points itself becomes your property that you're measuring. Right. So I just want to quickly state a few things from my understanding, and then we'll discuss a little bit more about the k-means clustering and choosing k itself.
Okay,
I'm actually
perfect.
going to draw a bunch of points if you can see them. Let me know. Yep, you're able to see them. That's
Yep.
great. Uh, so. Of course, it's only possible for us to visualize things in 2 and 3D, and extremely difficult in higher dimension. So here, what I'm showing is a bunch of dots on the 2D on a 2D screen.
Mhm.
Um, Very quickly, visually, it's immediately obvious to us that there are two clusters. I mean, maybe three if you partition some of these around. And we are interested in learning this. Why? So conceivably, each of these dots are a user within our social media network, and they conglomerate together based on some usage pattern, on some behavior they exhibit. So it would be helpful to learn these clusters. Again, we do not know the number of clusters that is in the data point ahead of time, but we progressively explore larger, higher and higher numbers of k, and we stop at certain stopping points. And here, the question, if I understood you correctly, is how do we decide or design that k, and what are some choices and what are some decisions around that?
Mhm.
So, all right. So one of the things I want to mention very quickly is visually we can do clustering so quickly because we have a notion of metric very quickly embedded in within our brains, and we are able to do that rather rapidly, especially in 2D and 3D cases.
Mhm.
So the problem statement then becomes, or the challenge then becomes, all right, let me just try to draw this here. If I were to, um, if I, in this particular case, if I were to choose k equal 1 as a starting point, what would I see? Well, by the way, I think before I even jump into that, maybe I should explain how k-means clustering or algorithm works, and what are the main steps involved in it, and then I'll explain what happens when k equal 1. So here, there are two specific steps that one needs to know. One is um, choice of cluster centroid, and assignment of I think I shouldn't say choice, I should say adjustment, assignment of data points to a cluster. So initially we start with, let's say our K is 1. What we do is we randomly, uh, within the space that we have, within the range, the support of this data matrix,
Uh-huh.
whatever the highest and largest values of K, of X and Y are, we choose a particular point. Did you have a question, Angie?
Yeah, so you wrote choice slash adjustment of cluster. Is that meant to be centroid or center?
Sorry about the typo. Centroid.
Ah, gotcha. Okay.
Um, right. So when we choose K equal 1, when we specify K equal 1, we randomly choose a point, and we choose this to be the centroid initially. Then we compute the distances to each of the data points, right? And then that distance squared, again, here I'm assuming some of these ideas that become immediately evident to us uh, without crystallizing them in terms of all of the possibilities of metrics and so on. So let's say we take the Euclidean distance, and then we take the sum of the squares of the Euclidean distance from the centroid point to each of these data points. I think that's not what I meant. We get a number, and this sum of squared errors uh, is a number that we can choose to guide our decision of K. What do we mean by that? So when K is 1, what initially we chosen a centroid, then we assign all points to the cluster centroid, right? Which means we say that all the data points belong to the centroid that we have chosen, marked by X. Then we compute this sum of squared distances. In this case, I'm assuming Euclidean distance just to get the conversation through and the idea across.
Mm-hmm.
And what would happen is, having chosen that, we come up with this metric. This gives us an estimate of error, if you want to call it that. Now, we can take the center of gravity of all these points, which essentially means average, right? Take the XY average for each of the dot points and then say, because all these points belong to this cluster now, I'm going to move this centroid to a, a point which is more uh, aligned with the data that we have. And this is the adjustment of the clusteroid step that happens. Okay,
Okay.
so you choose a cluster centroid, assign all the data points to that cluster, and move the centroid, and then you do this repeatedly until there is some settling that happens. Typically, the settling is a numeric. For K equal 1, you say settling. You say my centroid doesn't uh, moves by less than an epsilon, and that becomes my stopping point.
Right. So it's reached convergence essentially.
Exactly, some sort of a convergence, right? The convergence in here would be move between subsequent choices of centroid would be is with less than epsilon. Uh,
Okay.
right now, one thing some of your curious observers may have already observed that may have noticed that this may not be an evident thing. This is not an obvious thing that there may be a stopping point. There are certain criteria that are required for us to even go into being able to successfully run k-means clustering. But before I do that, I just want to quickly state what happens in a more interesting case where k equal 2. And then these steps become very evident.
Mm-hmm.
So let me mark those in a different color. Here we go. All right. Let's say k equal 2 now, and I want to strike this off. All right. K equal 2, and one of these centroids is here. I'm going to mark it up as C1, and the other centroid, let's assume for the sake of the conversation, is here, is C2. Now what happens is these words C1 and C2 were chosen arbitrarily, which is the first step. Right, then we look for each point. We look to see which is the centroid that it is closest to, and we assign membership for that data point to that particular cluster. So in this case, if I were to notate this particular data point as A would belong as a member of cluster centroid C2 if we look at Euclidean distance. Okay, and similarly, we go around every data point, and then we compute the distances for each one of these. We compute the SSE, the sum of squared errors for each of these data points. Okay. This sum of squared errors is only used at this point as a side fact, quote unquote, at this point, because we are subsequently going to see how we use this when we get to choose or decide on the K. Now, we have assigned A to C2, and in this case, none of the data points may be assigned to C1 because it's so far out. But then what happens in the second step? The C2 cluster centroid moves to the center of gravity, if you want, if that allows us a better mental image of what's happening. C2 moves to the center of gravity of the points that are assigned to it, to that cluster centroid. Once again, and in this case, C1 doesn't move, let's say. Once again, we go around every data point, compare their distances from the C2 to from the A to C2's new location and C1's new location. And let's say, for the sake of argument, that A is now closer to C1. And if that's the case, A would get assigned as a member of C1. And similarly, so on and so forth for every data point. So eventually, we would arrive at a situation where a bunch of points would get assigned or affiliated to C1, and the rest of the data points, in this case, there being only two, get assigned to C2. And again, how do we converge? We would say something along the lines of this. The move in our centroid locations, all of them, are within some epsilon. Right? And then that would be a convergence point for us. Now, remember that, more like it is conceivable that there is no convergence. And there are two key things to consider. One is convexity and isotropic. These are properties that are isotropic. These are properties that are expected off of the data points that we have in order for a k-means clustering algorithm to converge and have some sort of a reasonable centroids that are decided and detected. A quick example would be example of a set of data that may not converge is something along the lines of this. Imagine our data points are like this. Again, this is a little bit fabricated, but conceivably our data points are like this, in a circle, let's say, and some around like this. In this case, one may not be able to clearly say whether how many centroids, how many clusters are there. Although visually one might say, all right, these points in the middle belong to one cluster, and the ones outside may belong to a different cluster. But what we have done there is we have not used a distance metric. We have used our brain's power to actually intellectually see a pattern and then recognize that. And this would be a scenario in which convexity is not exhibited, because if you assign the outer ring to a cluster centroid C1 and the inner ring to a cluster centroid C2, any two data points that lie between two members on the outer ring do not necessarily belong to the outer ring.
Okay.
So there is a failure of convexity and isotropic characteristic in this particular data set. And the reason I'm mentioning this is one needs to be aware of the fact that this is possible, that one may not have a convergence. And I'm going to stop there and see whether you have any thoughts or questions, Anju.
So are you saying here that convexity implies that any 2 points in a given cluster, like for a line between those 2 points, any point on that line will also belong to the same cluster?
Exactly. So if you have two data points here, that's assumed in k-means clustering. If you have two data points in here, any data point between them should also be in the same cluster. Again, here I'm implicitly assuming some notion of a metric that is the Euclidean distance or Manhattan distance and so on. Sorry. So in this case, it is not the case. If I assign these two to a cluster, to one cluster, these points in between do not necessarily belong to the same cluster. But there are other techniques for that, and we won't get into that, like some techniques like DB scan and so on and so forth, that kind of address this kind of data scenario.
Right. Okay. And
What I want to focus. Go ahead,
would
please.
you mind also restating what isotropic means for us?
Oh, yes, definitely. So isotropic means a very quick way to have a mental notion of isotropic is that uh, the distance measure in every direction is the same. Not the definition of the distance, but the distance is, and I think I might be able to show this by um, having a set of points, maybe. So let's say these are the, again, if I can. Um, the distance measure in every direction becomes the same. And in this case, if let's assume uh, we have data such a way that they are not distributed in the same density in all directions, then we may not be able to learn. There may not be any convergence possible. And what I'm trying to show here is something along the lines of this. Um, and the this point, with respect to this point, the distance on these sides happen to be much closer, and on on the left side happens to be much farther. And in this case, one may not converge.
Mm-hmm.
Okay. And there are, one can construct synthetically pathological scenarios like these, but it's important to know that there are some caveats and just not simply jump into it. That would be my caution, right? Um, Applying several techniques may be a judicious thing to do. But I think I want to come back and bring the conversation back to selecting K, right? So my initial uh, explanation of what K-means does and what it attempts to learn and how this sum of squared errors number is computed now comes into play. So what one can imagine, or um, a simple heuristic, a simple mental notion that one can have is this. Let's just imagine every point where a cluster centroid by itself, right? What would be the SSE in that case be, right? What we're computing, SSE, is the sum of squared errors of the distance of each point from its cluster centroid. If each data point itself is the cluster centroid, the distance is zero. So SSE becomes zero,
Mm-hmm.
right? And at the other extreme, where K equal 1, it is the center of gravity or the center of mass of these data points. And that becomes the highest possible SSE, right?
Mm-hmm.
So one can intuitively think through this, think about the a plot of SSE versus again, no, ignore the fact that my axes and straight lines are in straight. The This is the K value on the x-axis, and on the y-axis, I'm attempting to plot SSE. At K equal 1, and of course K are discrete choices, K equal 1, we have some value that is the sum of squared errors from the center of gravity of all the points. And in fact, if one were to sit down and plot these out for most non-pathological situations, one would see a curve like this, which is the K, that the sum of squared errors would gradually go down eventually to zero if we run it sufficiently long. That is, the K number matches the number of data points
Mm-hmm.
to zero, right? And we would get a curve like this. The challenge in computers well, I want to say this is specifically within the world of machine learning and data sciences, is to identify a K where we have extracted possibly the maximal information out of this system, in the sense that we are not specifically learning the data set, memorizing the data set centroids per se, but we are gathering enough about the data. That is, we are not assigning centroids to every data point. That would be the extreme case. We are finding enough number of clusters as to have gathered sufficient amount of centroid information from it. And the way we do that, by the way, before I proceed, Angie, did you have any questions or thoughts?
No, that makes sense to me so far.
Okay. Um, is to study is to study the reduction in SSE as k increases. Typically, what is done, and this is a heuristic, typically what is done is we choose a point um, where we have gained or we have captured 90 to 95%, whatever the company or the team decides is their threshold in terms of uh, cutoff. So we might say, all right, I would like to get the number of the k number at which we have dipped down from the highest value of SSE by 90 or 95%, in the sense that we have at that point exhausted extractable centroid
Mhm.
information. A more appealing, and this, of course, these thresholds can vary and so on. A more appealing and visually appealing and uh, easy way to recognize this is to run this k-means clustering. Bless
Thanks.
you. Run the k-means clustering algorithm for various values of k, progressively increasing. So you just start with 1, 2, 3, and so on and so forth, and then visually inspect this plot. So as we said, we can compute SSC score, visually inspect the plot. Typically what happens is, and again, this could vary from domain to domain. It could vary from data set to data set. Typically what we would find is there is a point at which the curve tapers off. And this is what we call the elbow point. Because a larger K yields us relatively smaller marginal improvements in SSE reduction. Okay, and that's why this common method is known as the elbow method, and you can visually uh, capture that. Um, Also, if you wanted to be wanted to apply some sort of a machinery and not look at these plots, it's also possible one could look at the decrement in SSE between successive points and pick the one where we start seeing the least amount, drastically least amount decrement in
Mhm.
SSE, and that would also be
So,
possible. But I think it's yeah. In a regular normal cases, we can actually visually pick the k, or if the team has a choice of 90 to 95% or whatever the numbers are for the data set, pick that as well. I'm going to stop here. I believe you
oh
had a
yeah, so I
question.
was just restating. So it seems like the elbow just marks the point at which the you start getting less and less like marginal utility from increasing the K, right? Mhm.
Right. We are entering into the terrain of
Right.
memorizing the data in
Yeah.
some sense, right? We're actually
Yeah.
learning some
Okay.
things. Yeah. Um, Yeah, and I quickly wanted to mention a few things. K-means has been used in quite a few places for a lot of things that typically one may not immediately or viscerally apply to, and which I believe some of the folks may find
Mhm.
helpful. For example, let's say we have a large data set, lots of rows of data, and one thing invariably that you find in large data sets is missing values. How is it that we can assign values to the missing records for particular features? Well, one way to look at this would be to study the k-means clustering nature behavior of the data that we have, which is for the data points
Mhm.
which contain all the features, and then uh, in that data plot, project or figure out where our data points are, which are missing the features, and assign the mean value of the cluster centroid to
Mhm.
that data point. And that has actually been used quite well in large data sets to great advantage to actually improve feature coverage and subsequently for machine learning, supervised learning on these data points for its particular objective or a prediction target. Um, Anyway, I'm gonna stop there. Did you have any
That's
questions?
so far. Yeah, I'd love to hear if you have any other suggestions for other ways to select the best K.
Yeah, so there are other techniques which I've only briefly used a silhouette score based. technique, in which you define a silhouette score for each data point, uh, and the silhouette score ranges from -1 to 1. If the silhouette score is negative, it typically means that the data point you're looking at has been
Okay.
misassigned to to a cluster. And again, there are some libraries that explicitly implement these. Um, and if it's a negative silhouette score is positive, then that means the data point has been properly assigned to the correct cluster.
Does that imply
And
that you have some way of determining what is the correct or incorrect cluster then?
yeah, and there is a specific formulation for that, which is you compute the uh, silhouette score, and you can look it up online as well. Silhouette score um, is the average distance of a particular point I to all the points in the same cluster, minus the average distance to all points in the neighboring cluster. I think it's the other way around.
Mhm.
The distance to the neighboring cluster minus the distance to the cluster that I've been assigned, and then divided by the by the maximum of these two. So that gives you a fractional number, right? And that's used to
Okay.
see whether this particular point has been correctly assigned. And one could go and compute this across the board, right?
Well, I
And
guess
take
that
an
kind of
average.
implies then that the higher the score, the larger the distance to the nearest cluster, and the smallest the distance to the centroid of the same cluster.
Uh, Right. You are measuring the distance not to the cluster, the centroid. You're measuring the distance of
Okay.
individual data point to every data point in the neighboring cluster.
Oh, gotcha. Okay.
All right. So it is not directly to the cluster centroids.
Mhm.
So I think visual, once you draw it out visually, it might make sense to see why this is different from the cluster centroid distance, because there essentially what it's attempting to capture is proximity to the edges of uh, for those points which are on the edge between two cluster centroids. It's conceivable that that point could as well be put in one bucket or the other, and then that forms gives us a silhouette score. And you take the score across all the data points, it'd give you a number between -1 and 1.
Right.
And
Yeah. So it's kind of like it's implying that the clusters should be more like tight or more dense, and then far away from other clusters.
yes, there is some geometric interpretation you can make, which is the cluster. If you want to look at it, describe it as variance or so, the cluster variance is narrower. There is some structure like that that's implicitly being assumed by that silhouette score. Yeah, and then based on that, then you can use that as well. Plots, silhouette score plots, I think, and then I've used it once or twice. But most commonly, what I have seen in the industry, and specifically talking about social media content and users, and social media users and so on, we use k-means clustering,
Mhm.
and of course, we may not directly upfront use k-means clustering directly on the data points, because in the high dimensional space. It may not be the case that the distances are much larger in higher dimensional spaces, and it may not be beneficial to run a k-means cluster in that space. What we do is project it down to
Mhm.
a lower dimensional space, like a 2D or a 3D, using some sort of a algorithm like TSNE or a PCA and so on. And but once you bring it down, then run your k-means clustering, and that gives you uh, that gives you an idea of how many clusters are there in the original data set in this high dimensional space.
Okay.
So computationally wise, it is reduced now. Computational effort is reduced because one of the first things that we do is project down the high dimension data to a lower dimension. Then you compute the cluster of centroids in the lower dimension.
So I imagine then that if you're projecting the data from a very high dimensional space to a lower dimensional space, that may not be like a linear transformation. So maybe that might actually change the distance metric you want to use.
So that is true. Thank you for bringing that up. The When you project it from a higher dimensional to lower dimension, you can use linear transformations like PCA and so on, or you could actually
Mhm.
use nonlinear transformation like TSNE. And you're right, but there are distinct properties and characteristics and promises that are made by such. And of course, we need to closely examine which specific dimensionality reduction technique you want to use. But they, in general, tend to retain the relative distances in such a way that the shapes of the original data are preserved. Specifically, TSNE does that. Okay, so and that's why TSNE is helpful as well. It's nonlinear dimensionality reduction, and then you can now apply k-means clustering on that. Yes, the distance that you measure in the lower dimension is not exactly transferable to the higher dimension, but there is some correlation between the two of them.
Okay, sounds great. So I think this is a great place to pause. This was fantastic. We've learned so much from you. So I'd love to hear from you. If you were to analyze this interview as if you were the interviewer, what do you think went well, and what do you think you might do a little differently?
Based on what we just discussed, I believe we have covered the gamut of what k-means clustering does. We also spoke briefly about some of the conditions or criteria that one needs to be careful about uh, jumping into k-means clustering when specifically when we do not find convergence or at least be aware of the fact that there are non-convergence as possible. So I think we've covered the gamut of that. We've also gone through a visually how one would choose a suitable value for k using an elbow method. And I think that that's the good portion. What is it that we could perhaps do better is perhaps we could explore other techniques like silhouette score, elaborate a little bit more on that, with some diagrams that explain what the scores are and how that might be different from the k-means in using elbow method. And there are several other methods as well, and I don't think we got a chance to look at that.
Yeah, that makes sense. I really enjoyed how thorough you were in explaining everything, even though the question was precisely about choosing K and you didn't actually need to implement the K-means algorithm. I really appreciated that you went in depth into explaining like what the K-means algorithm actually does, because that is relevant for how you select K. And I felt that the visual diagrams too really helped explain the intuitions behind how it worked. And I really liked that you covered like multiple different methods for selecting K too. You didn't focus on just one. Yeah, so I think maybe it would have also helped to maybe like make sure you define all of your terms before using them, like isotropic. That may not that helps like demonstrate exactly like what you're talking about, because you know the interviewer might know, but they also might not, and they probably also just want to see you explain it.
Hmm.
Um, yeah, and then the last thing is also like when you're explaining things like silhouette score, you're mentioning that okay, this silhouette score is based off of whether or not each point is correctly classified. Helps to explain what you mean by like correct in this case, because we did mention earlier that it's an unsupervised problem, so we don't actually have the labels. And then I think once you explained it, it was a lot more clear, and that's something that we can also write down like the formula for example. So yeah, how does that
That's
sound?
true. Yeah, yeah. I think that those are
Yeah.
valid feedback. Obviously.
Mhm.
Thank you.
Yeah. Otherwise, this was super educational. Thank you for being here, Vikram. Yeah, and thanks everybody for watching. Be sure to check out Exponent's new machine learning course, and good luck on any upcoming interviews you might have. Bye, everyone.